The claim that creatine HCl allows you to take a smaller dose than monohydrate requires a specific mathematical examination. When you do the arithmetic, the claim collapses. Creatine monohydrate is creatine with one water molecule attached. The molecular weight of creatine is 131 grams per mole. The molecular weight of water is 18 grams per mole. Creatine monohydrate therefore has a molecular weight of 149 grams per mole. The proportion of that weight that is actual creatine is 131 divided by 149, which equals approximately 88%. 1 gram of creatine monohydrate contains approximately 880 milligrams of creatine. Creatine HCl is creatine with a hydrochloric acid molecule attached. The molecular weight of hydrochloric acid is 36.5 grams per mole. Creatine HCl therefore has a molecular weight of approximately 167.5 grams per mole. The proportion of that weight that is actual creatine is 131 divided by 167.5, which equals approximately 78%. 1 gram of creatine HCl contains approximately 780 milligrams of creatine. To deliver 5 grams of actual creatine using monohydrate, you need approximately 5.7 grams of product. To deliver 5 grams of actual creatine using HCl, you need approximately 6.4 grams of product. HCl requires more product by weight, not less, to deliver the same creatine dose. Yet creatine HCl products are routinely marketed at doses of 1 to 2 grams per day, fractions of the 5-gram monohydrate standard. At 1 gram of HCl per day, you are delivering approximately 780 milligrams of actual creatine. That is less than 1/5 of the dose used in the monohydrate research that established the performance benefits. The claim that a small HCl dose produces equivalent muscle loading to a standard monohydrate dose cannot be made on the basis of molecular weight or absorption arguments. The math does not support it, and the clinical evidence does not support it. The bioavailability argument attempts to rescue the small dose claim by asserting that HCl's superior solubility produces a proportionally higher fraction of the dose reaching muscle tissue. For this to work, HCl would need to be absorbed so much more completely than monohydrate that a 78% creatine product at 1 gram could match an 88% creatine product at 5 grams. Monohydrate absorption is already estimated at greater than 90%. The mathematics of making that gap close by improving absorption are not credible. If you choose creatine HCl based on a genuine preference for the dissolved texture or for other personal reasons, the appropriate dose is one that delivers equivalent actual creatine to what the monohydrate research uses, meaning 5 to 6 grams of HCl product per day, not 1 gram. Check the creatine content per gram of your specific product, then dose accordingly. The practical implication of the dose math becomes clear when you examine what someone who follows the 1 gram HCl protocol is actually achieving. At 1 gram of creatine HCl per day, they are delivering approximately 780 milligrams of actual creatine. Over a week, that is approximately 5.5 grams of total creatine delivered. Over a month, approximately 23 grams. Standard monohydrate at 5 grams per day delivers approximately 4.4 grams of actual creatine. Over a week, approximately 31 grams. Over a month, approximately 135 grams. The monohydrate protocol delivers approximately 6 times more creatine per month than the 1 gram HCl protocol. Muscle creatine loading research has established that the benefits of creatine supplementation, increased phosphocreatine stores, improved power output, enhanced recovery, occur because muscle creatine levels increase meaningfully above baseline. The doses in the research literature that establish these benefits are 3 to 5 grams per day for the standard protocol, or 20 to 25 grams per day for the loading phase, both expressed in terms of actual creatine delivered. These doses come from studies using creatine monohydrate. The 1 gram HCl protocol does not approach these doses. Research on low-dose creatine supplementation, below 2 grams per day of actual creatine, does not show the same muscle loading outcomes as research at standard doses. The transporter takes time to saturate muscle creatine, and at low delivery rates, the rate-limiting step is simply how much creatine is presented to the transporter per day. Subtherapeutic dosing produces subtherapeutic loading.